There it is. All right, hi everyone. So before we get started, we should announce that we have a feedback form since we're at sort of a midpoint in the semester where Alan's 4 weeks of like computer architecture content over, and now we're moving into my side of sort of scientific computing and how you use these things as more of an end result. So Alan, could you at some point during this just drop that link in the chat and put it on the Discord later?
Yes, I will drop it in the link in the chat, and I'll drop it in the Discord.
Yeah, it's pretty short. It's just like, what do you think of each component of this class? Lecture office hours, discussion, there's no discussion, lecture office hours, homework, and just general feedback on those things. But yeah, we could use some feedback from you guys on how you think this is being run, because we're at sort of the natural midway point. Okay, with that, let's get into today's lecture, which is a really exciting topic.
Feedback form is anonymous, by the way.
Oh yeah, it is anonymous. Yeah, okay. Let's get into today's lecture, which is all about the Julia programming language and how you can code efficiently. Coding efficiently is a really big topic, of course, and we're going to talk about multiple facets of it. And this is really only just one of them, but it's our starting point. So the first question you might ask when I tell you we're introducing a new programming language is, why do I want that? Like, Python works perfectly well, and everyone's talking about how good Python is for scientific computing out there. Everywhere you look, people are telling you you should learn Python if you want to get into research. So what's the problem with that? And there's a lot of good things about Python that we've made use of in the first part of this class. It's really easy to understand relative to other languages. You can make quick demos with Jupyter notebooks, and lots of people write in it. So there's a lot of really good other packages out there and lots of support. Why not use it for everything? And you might have, okay, this might be interesting. Any ideas on why that might be? Put it in the chat or say it out loud. We've run into a couple of them in the first several weeks. Speed's a really good one, yeah. Well, we sort of resolved that with numbers JIT function, but then we found that that didn't work on everything. And we sort of resolved that with a bunch of workarounds like offloading the GPUs and a bunch of other things. But ultimately, they're all just sort of patches on top of the fact that Python is inherently not very fast. It goes for expressibility over speed. And there's other languages out there like C and Fortran and stuff like that that go for speed over expressibility. And so you get into, like, among just speed, you get into these other issues. It's dynamically typed. Remember how when we were doing number.jit, you had to recompile for every type? So because Python is so flexible in the way it writes things, it comes at a disadvantage because there's not a lot you can do statically. Every time you run something, you have to rerun it from the start with no lasting memory if you're not running it in just-in-time compiled mode. It also doesn't allow us much direct access to how things actually work. We built up this whole mental model through talking about computer architecture of what's actually happening under the hood, but there's very little of that you get to interact with in Python itself. You get access to a list. You do not get access to actual memory blocks that make up an array. And that can be a good thing because of this idea of abstraction barriers of, I don't want to be able to see things. I just want you to optimize them under the hood for me. As a physicist using a programming language, I don't want to have to think about memory allocation all the time. But the fact that you sort of end up going too far with that, and you lose a lot of potential power that you can leverage for science. Also, if you start working on big projects, you'll find that there's a whole lot of issues with Python environment setup. We had this discussion when we were setting up the environments initially for this class about, should we use Conda or a virtual environment or a Docker image or something else? And there's a lot of solutions out there and a lot of people use these things differently. There's no real standard and it's just a bit annoying. And vectorized operations are unintuitive and you have to sort of tailor your code to a specific way of thinking with NumPy. And that can be helpful, but that can also harm, again, expressing your ideas in code, which is really the goal if you're a physicist rather than a computer scientist or software engineer. So maybe based on running into these issues, we start building up a wish list. I want something that's compiled, well, JIT compiled the same way number was, but I still want to keep scripting in notebooks. I don't want to go to C Fortran levels of just raw code and manipulating memory pointers, whatever it is those people do. I want to keep the intuitive syntax. I really like how Python does syntax, but I don't want to lose out in speed because of it. I want to be able to feel like I'm writing still in a dynamic language, but really have static typing going on under the hood for compile time speed. I want to be able to access data structures directly when I need it, but not to worry about it when I don't. Python's pretty easy to debug compared to some of those other languages out there. So I want, if I have an error, maybe I want to be able to go back to say, this is a specific line, or this is the chain of what I did. I also want to prove it's a package management, environment management, and you can imagine listing all of these things. And I would sort of sum them up into this little neat phrase of, when you have a problem, there should be an easy solution. And when you don't have a problem, you shouldn't have to think about it at all. So a bunch of computer scientists, almost 10 years ago now, it was about 2012, a bunch of computer scientists at MIT got together and they said, we have all these problems. Let's try and make one language that does all of this. And so Julia comes into the picture. Essentially, you can get an idea from this quote. They got together, they made it a wish list like the one we had on the last slide of, this is a bunch of things that I really like about all these other languages. How do I combine them into one? And they admit, we're greedy. This is like a lot to ask. And it took a lot of work on their end and the development of a really big, like, independent open source developer community. But wait, I don't think I can hold up.
It was
that's valid.
Yeah.
Okay. Yeah, I have chat on my other window now, so on my other monitor now. Oh, are you not able to hear? Can you hear me right now? No. Anyone else? Can you hear? Okay.
I
can hear.
I can also hear you.
Okay, good. So it seems like it's good for most of us, and for Christian, you can just check out the recording later. Yeah. Or hopefully it just comes back on its own. I don't know. Zoom's weird sometimes. Anyway, they got together and they made the language of their dreams. So what does it actually do? The first natural question you might ask is, oh, that's another slide from now. Oops. Yeah, maybe try leaving and joining. If you look at the actual features of Julia, it has a lot of these things on our wish list. Remember how Python wasn't fully JIT compiled when we were just adding number.jit everywhere? There were some like weird things that you still couldn't compile. Julia is written to be only just-in-time compiled. That's a core part of how you develop using it. It's got static typing when you need to specify it and dynamic otherwise, very similar to how it worked with number. The syntax is pretty similar to Python. We're going to see in the back half of this lecture. Okay, yeah, Christian says you can hear it again. Awesome. Yeah. We're going to see some actual Julia code in a bit, and you'll see, I hope that it's like pretty similar to Python and how easily you can read it as like a sequence of commands. It's really easy to vectorize custom operations. The speed's really good because JIT, it fixes package management and environment management problems and not alids left. Oops. And here's an interesting one. There's this feature called multiple dispatch. And I was saying just before lecture, if you'd asked me 6 months ago, because I'm still just actively learning about this and teaching myself this language mostly, if you'd asked me 6 months ago, what's the best feature of Julia, I would have said, oh, it's really fast, but it's got like Python-like syntax. Now I'm going to say multiple dispatch. So, and that might be a weird thing because it is kind of like an obscure feature, but we're going to get to what it is and why it's cool. Anyway, a natural question to ask when I tell you this language is really fast is how fast? So in anticipation of this question, the Julia developers put together this nice little graphic of down here, they've got like common languages that are used for science or anything else. And their benchmark is C. C is 1 unit of speed. Right over here, we've got Python. And that's Python with NumPy. And it's still like, at worst, 100 times slower than C. Like it's pretty fast in matrix multiplication because Python matrix multiplication basically just calls C under the hood, or NumPy does. But most of them, they're in the like 10 to 100 times slower. Mathematica, another one you might have seen for physics purposes, way over here, not very fast. MATLAB, a little better on average, not very good still. And there's Octave all the way over here. And as you go further and further left, you get to more obscure computer sciencey things. And then you have Julia over here with like really minimal spread. It does better on this one, the Mandelbrot set operation, than C does. It's exactly on par iteration pi sum, which is the like, if you do sum of inverse squares, yeah, it's normalized to C. C is 1 unit of speed here. And like all the rest, it's pretty comparable. Maybe you'd get like a factor of 2 or 3 loss. You know, pretty good for the syntax improvements that I'm claiming. You're probably not going to notice that last little bit of performance. So it's right up there. And I'll show you actually a really cool application of that in a bit. Another thing is it's got like full math support. So this is something that I just grabbed from a friend's robotics package. I knew nothing about robotics, and he just had this pretty much in like Jupyter Notebook style of like, this is the math that you use, and this is how it's translated to code. And it's pretty much one-to-one. I felt like I didn't have the sense of I have to learn the specifics of how this is working. And that really helps with the idea of an abstraction barrier. I don't have to think about how this is implemented under the hood. I just have to learn the math, because you do need some amount of learning, but I focus on learning the science or the ideas behind it rather than the coding details. And then I pretty much have the same operations. So you can type in LaTeX, and I'll demonstrate that in a bit. And everything just looks exactly like it would on the page. So even though I know robotics, and like, albeit because this is pretty well commented as well, it's a lot more natural than the Python would be, I feel. Okay, now for what multiple dispatch is. Now, when I just describe it to you, it doesn't necessarily seem like a revolutionary idea, but it does change everything. And they even have a talk over here that says, it's unreasonably effective. It's like the most powerful feature of the language. So what is it? Essentially, the idea is instead of a single function, I can make a function that has a bunch of methods within it. And it specifies which method you use based on the data types of the inputs you passed in. So for example, if I put in the asterisk, the star for multiplication, based on the context, it'll understand that that means multiplying 2 numbers together or multiplying 2 matrices together. I can put in A star B, and it'll infer based on the types of A and B what this is supposed to be. And what this does is it makes it really easy to enable code along with when you use it in conjunction with what I'm going to call a hierarchical typing system that I'll show you in a bit. It basically means when I type in A star B, I don't have to think about if this is the case, then do this, if that is the case, then that. And so that allows me to compose things really easily. It allows for separation between high-level algorithms and low-level details, because I don't have to care about how the star operation is implemented. I just have to care that it'll do its job. So that can seem a little abstract. So here's an example. Suppose I'm writing a function in Python called countlines. Can you see my zoom bar? Is that obscuring any code? Seems like we're okay. Okay. Yeah. Suppose I'm writing this function called countlines, where I want to open up a text file and read it and count the number of lines in it. And you see that there's all these like if then else cases going on. And this is an example I got from this Medium article, by the way. So you start off with this function file lines, which, this is decent easy to read this bit. You open up the file, you read them all, and you get something that has a length. And that's the number of lines. You close it and you return the number of lines. Okay, seems straightforward enough. But then you have to account for different cases. If you actually have a list of file names being passed in, you have to call this function file lines in every single one of them. Otherwise, if it's the name of a single file, you call file lines. Or if there's 2 arguments, then you infer the second one is an extension, and you have to check if it ends with the right thing, and it just spirals sort of out of control. You have no idea what's going on and what's going to happen in a specific case looking at this function, unless you like sit down with a pencil and paper and really trace it out really carefully. And it's just kind of annoying. If I have a bug in this, I don't know where to look until I do that step of sitting around thinking about it. So can we do better? And here's how Julia does it. So this first function is pretty much the same, but I don't have to name it something different anymore because of this overloading. So you see I've got the same function count lines 4 times, but really that means I'm defining one function with 4 methods based on what the inputs are. And now I see really clearly what's happening. I do this same thing that I did before in the Python file lines for this first one. If it's an array of file names, then I call count lines, which now refers to this one, on each of those. If it's got files and extensions, then I do a filter and I count lines on the filtered list, and that calls up to this and up to that. And so it just works a lot more easily. And now if I have a bug in this, if I have a bug in the case where I'm calling it with a list of file names and an extension, then I know I need to look over here. It's a lot easier for the human eye to process and a lot easier to debug with. And there's a lot less code reuse. So that's the high-level idea of multiple dispatch. And the next natural question from there is, how's this used in science? And this is sort of the standard example that's used for that, which is differential equations and measurements. So these are 2 packages written in Julia. Team A over here wrote the differential equations package to, it does feel like cheating a bit, but, it works. It's just great design. Yeah. Team A wrote differential equations.jl. .jl is the extension like .py for Julia, which is a library to solve differential equations, set up and solve them. And you see sort of the workflow over here of you write a function called pendulum that defines this like the usual differential equation for that. This should be a sine theta, but that's fine. What's the point of solving something numerically if you're just gonna do something that you could do analytically? But whatever. Let's go with it. So anyway, Team A wrote differential equations.jl, which is something that solves differential equations on generic numbers. And number is an abstract type. It's just, you can't define a number specifically, but you can define subclasses of numbers like integers and floating point numbers and things like that, and they'll all be numbers. Team B made a package called measurements, which introduces the idea of a measurement, a specific type of number that has error bars on it. So like over here, we've got the pi over 60 plus or minus 0.01, or the length of 1.00 plus or minus 0.01. And teams A and B didn't talk to each other at all. They didn't know the other one existed. But their code put together work perfectly. All I have to do to turn this from a differential equation solver to a differential equation solver with uncertainties is put plus and minus bars on these things. Now, these things are measurements. And if somewhere inside differential equations.jl, I had to multiply 2 measurements, measurements tells me how to do that. And I don't have to specify that it's a measurement being multiplied because of multiple dispatch. It just all works seamlessly. Yeah. Okay. Multiple dispatch, I think, is really well aligned with scientific ways of working. We tend to think a lot in terms of functions, in terms of like input-output boxes. And we want to think more about ideas, about like the high level of what an algorithm is doing, than the low level of how it's implemented and how you allocate memory and that kind of thing. And so while it's a weird idea for like most programming use cases, it's a really natural fit to a lot of science, because I don't want to care whether I'm doing multiplication between ints and floats or floats and floats. I just want to care that I'm doing multiplication. I want to be able to write math down on paper and write it in code like pretty almost unchanged and get out useful results. And so this is what makes it a really good science language. Remember, and I feel like I've brought up this point a few times, but let's bring it home. Way back in lecture 1, we talked about one of the big ideas being abstraction barriers. I don't want to think about something that I don't have to think about, that the computer should take care of for me. And Julia lets us do this because it lets us just express our ideas the way we want to, the way we do it on paper. The idea of here's how my differential equation solver works is entirely separable from here's how to handle errors on measurement. They didn't even, like, again, it's just so amazing that they didn't even realize that they had this interoperable functionality. It was just like a nice surprise that came up. Someone wondered one day, oh, I wonder if I could just plug a measurement into a differential equation solver, and they did it and it worked. And so the combination of really good speed, being able to express ideas naturally, and writing modular code that does like a little bit that's easy to test at a time comes together just really beautifully. Okay. I should also mention Pluto notebooks. These are used as sort of a replacement for Jupyter notebooks, going more remote in the solar system. And this is pretty much how they work. We're not going to use them in this class because I found they have some issues cross-platform. It's not as big of a developer community as Jupyter does. But essentially, here's how they work. They're a version of Jupyter notebooks that have consistent state. What that means is, in Jupyter, if you ran a cell and then ran a different cell that depended on that first one, and then you changed the first cell and reran it, you'd have like an inconsistent state in the middle there, meaning your second cell wouldn't update to match. It would still think, oh, I have that first level in like a hidden state. So if I said like a is 3, tell me what a squared is, I get 9, and then I go back and change a is 4. Now I've got a state where I've got a is 4, a squared is 9. And that just seems, that's just obviously wrong. And that's not really good for reproducible science. So we're going to stick to Jupyter. Lots of people like Pluto, and do give it a try and see if it works better for you. Okay. And here's a really cool application that I'd like to talk about. One of the things that I came across while I was looking into if I should use Julia for my own research. There's this thing called the Sloan Digital Sky Survey. It's basically like a map of the entire universe, all the galaxies and stars and stuff that we can see out there. And so the science task based on all that data that it collected is go pixel by pixel and identify what the objects are, whether they're galaxies or whether they're stars, and if they're galaxies, are they elliptical or spiral, and if they're stars, what type do they have, and fit all kinds of other parameters of that to do the point spread function. And so they came up with the statistics of how to do that. And so what they did is they had this massive problem because the entire sky is like really big, not surprisingly. So they had this variational inference problem, which is just like, you just have to understand fancy statistics with 8 billion free parameters, which is just like massively out of whatever we can conceptualize. And at the end of it, they made 188 billion stars and galaxies. They made a catalog of that many. They didn't make that many stars and galaxies. They made this massive catalog out of 178 terabytes of data. And they did it in 15 minutes of computation time. Granted, on one of the biggest supercomputers in the world, but very few languages have ever gotten there. These are the ones: C, C++, Fortran, and assembly. And that talk over there is really fun. I can send it to you later on all the little tricks. And actually, this was like a 2-year project, I think, 2015 to 2017, which was years like 3 to 5 of Julia. So a lot of Julia was developed by doing this. It's still a relatively young language, and there's a lot still to do on like the core packages out there. So they fix issues and build out functionality as they need it, pretty much. Okay. Now, all of this sounds great, but is it really worth switching away from Python? Because we're used to Python, and we've been doing Python-based homeworks for like half of the class now, nearly. So why switch away halfway through for our purposes? And of course, there's a point of it's really easy to express things that I've made several times now, and the speed up. But it also ties into one of the other core tenets that we want to bring into this class. Really often when you're learning computer science, or when you're learning computer science or physics or astronomy more specifically, you'll get told, oh, you have to learn such and such language for this. And you're like, oh my God, I have no idea how to learn IDL. I only know Python. And that can seem scary the first time you're doing it. So But it's not actually that different. It's just a different way of writing down the same ideas. And no individual way of writing down the ideas is more important than internalizing those ideas themselves. Languages don't matter, ideas do. So in that spirit, CS61B tells you languages don't matter, the ideas behind them do. And to prove it, you're going to go learn Java right now by doing like an introductory project. And that's because that's the best tool that they can find to express their ideas about data structures and algorithms. And so for us, that is Julia. We're obviously not going to do a 61B scale style of introduction, but we also have like less of a barrier to cross because Python's a lot more similar to Julia than it is to Java. And so you'll get some practice picking up these new things. And so when you have to do that on a real research project, it's going to make it that much easier for you. Okay. Disclaimer is it's not a totally perfect language. I used to present this as a totally perfect language, and all my friends were very annoyed with me because I would never shut up about it. It's like been a serious social problem for me. But yeah, I've come around to it's a really good language, but it's a tool, and it's one of many tools in your toolbox, and you need to know when to deploy the right one. The main thing is it's just-in-time compiled. And what you might remember from our just-in-time compilation demonstrations before is you had a little bit of a wait. And in fact, when we go into this Jupyter notebook in a minute, we are going to see small waits. The first time you run code is going to take a while. After that, it's going to be basically instant. This makes it really well suited to big science problems where I don't really care about the one-time execution cost, and I only care about the execution cost over the whole thing. And we're going to see that a little more formally when we do asymptotic analysis probably next week. But if you do only have like a really simple use case, something that's more naturally done in Python, I want to fit like 20 data points or something, that is probably, or I just want to make a really quick plot of like x against x squared, something that's like really easy and quick to do. Python's probably going to be a better bet because just loading up the packages you need for that in Julia is going to take longer than it would in Python. So there's this link here of someone who wanted to plot COVID-19 data, and I'll just drop the link to this in the chat if you want to read that later. And who was like, oh, this Julia thing seems pretty cool. Let me try and use that. And they ran into some issues with things taking a long time, and then they just opened up Python and it worked like a charm. So it's a good tool. It's not the best tool. It's one more thing that we're going to add to our arsenal. Okay. There's a lot of other classes and texts out there that use Julia if you want to learn more about how it's used in the real world. Some of them have been inspirations for me in setting this up, these first two especially. MIT's 18.S191 is like it structures as a first semester CS class, and it's taught by the original MIT professors who made Julia, and also by Grant Sanderson, who you might know from 3B1 Brown. So that's really exciting. Then this class at Penn State, a graduate level class in scientific computing. I've like borrowed the general structure of it for this decal. At Berkeley, Math 124, which I almost took this semester, is another like mathematical introduction to CS, and it uses Julia. And there's a couple others over here, and Julia's own website has a bunch of them. Let's drop this link in here too. And there's Think Julia textbook. Okay. And now we're going to go into an interactive session. I've been talking about this language for a while. Now it's time to actually see what it looks like. So I'm going to cover the basic features and how they look different than Python, variables and checking types in functions, a really simple example of multiple dispatch and how that makes sense, how you do loops with a range object, conditionals, and the couple nice syntax tricks that I like. Okay. Right. Before we get started on the coding, are there any questions? Okay, seems like we're good. This didn't totally clear. Anyway, so the first thing, oh, wait, can everyone see this okay? Okay, I'm seeing nods. That seems good. So the first thing is, let's get a look at what the syntax looks like. So this is how you define a function in Julia, and it looks pretty similar to me to the Python. You have the general structure of like function, and then the name of the function and its arguments. You have like an if else in there, you return with the keyword return. All of that's similar. What's different is every time you start something like a loop or a conditional or a function, you have to end it with the keyword end. And this is a lot nicer and is one of the things that people are really annoyed about at Python when they get started with it. Because in Python, you do this implicitly with like indentation. You do something like, I can't actually write in Python here, but you do like def factorial n, and then I have to tab out here for if n equal to 0, that kind of thing. And if I get this number of, if I don't tab right, I get this number of spaces wrong, you try and run this code and you're set up for spaces, not tabs, it's all going to crash and be like inconsistent use of indentation, something like that. None of that with Julia, none of that with most other languages, in fact. Python's use of white space as an actual meaningful thing is kind of weird and depends a lot on you having good style. So this is a bit of a nicer guarantee. I have a function, I end it. I have an if, I have maybe an else if and else in there, but I end it. Okay. Another thing is this bar means or, and an ampersand means and. So let's write those. And this is more in line with the general coding convention that you'll see in other languages as well. Put backticks around that just to be really clear. Python's use of the actual words or and is, again, kind of an oddity in the scope of other programming languages that are out there. Most of the time you'll see something like this. You'll see like double bar or double ampersand. I think even Python supports double bar and double ampersand. But yeah, this is the only way to do those. It doesn't? Oh.
It's very confusing to a C programmer like me.
Yeah. Yeah, but C has it, Java has it like this. So this is more in line with convention. You return the same way. And we also didn't have the colon here because you don't really need it. You know that you're starting a function because you just wrote the word function. But otherwise, it seems pretty similar. It's else if instead of elif. And that's really about it for the basics. So let's run this. And you see there is a bit of a wait. Again, this is not necessarily really small things. Again, probably best done in Python because we do have this little bit of a waiting time while it compiles. But now it's done and we can start running it. And if you remember again from our number part, this first run might also take a while. And it'll see, oh, look, it's an invalid input. And this shouldn't really be surprising because, you know, you see it goes through. It's not 0 and it's not 1. It is less than 0. So it reads an invalid input. And this run should be a lot faster. It was a lot faster because now it's calling on this compiled code. Okay. So here it's arrays and loops. In Julia, everything's an array. There's no such thing as a separate array in a list like Python has. But you do have to be careful because the better guarantees you can put on data types of things, the faster everything is going to be. Remember, it does for the memory allocation reasons that we discussed in previous lectures. So this is like, and it's not really a problem because it's like a really small snippet, but I haven't specified a data type for this. And you'll see that its data type here is any. It could be anything. And so it doesn't know up front how much memory to allocate for the answers of what it's going to get here. And that makes it slower. But anyway, here's a for loop. This is the same thing as a Python range from 1 to 10. And this is the same thing as an append. Whenever you've got a function in Julia that has this exclamation mark, it means it's changing its inputs. It's an impure function. So in this case, I'm pushing factorial I onto this array of facts. Julia is also one indexed, which is kind of weird. It's in line with MATLAB convention and not actually most programming languages. Most use cases, this is fine. Because again, I don't want to have to think about how numbering memory actually starts at 0. I just want to think about like numbering things in whatever way makes sense as a scientist. But there is a package to like arbitrarily offset your numbering of arrays if you really want to. Okay. Another thing is vectorization is a lot nicer. Before in Python, when I had to vectorize something, I'd have to do this, or I'd have to like write a list comprehension or something like that, or I'd have to rewrite how I write my function. the last one probably more so than the others, so that it would run faster. And it's all a bit unnatural, and there's a lot of like NP dots and things, and I have to explicitly factorize and things. In Julia, that's just all done with a dot operator. If I can specify something over a single input over here, if I can just do like factorial of 3 over here, then I do a factorial dot over a list of things. In this case, that's a range, but I could also do something like factorial dot 3, 4, 5, and it'll apply itself to each one. Yeah. Also, if you go on the interpreter version of Julia, which is probably where you'll be running most things in like a real code base, that is a fair bit faster than it is here. Just I think the Jupyter adds some extra runtime to it. So yeah, dot vectorization is just a really nice feature and a really good way to specify if you're operating on a single thing or multiple things. Because that also gets to be a problem. If I had this array saved elsewhere as A, and I call factorial of A, I don't know, is this a factorial of a number or is it a factorial of an array? Don't have that ambiguity here because I've got the dot. Okay. Next up, static and dynamic typing, how it handles that. Let's say I write a function named square all. And once again, it's defined by function, the name of the function, argument, return this thing, and end. And I have to end, but it doesn't really care if I indent it to whatever level. Just conventionally, you should still indent it like one at a time, like we've been doing, but it doesn't really care. Oh, also, you have the caret for square now. And so if I square 3, I get 9 like I'd expect. And if I raise a string to the power of 2, it's going to repeat that string, which is kind of interesting behavior. And that's just one of their, they put some thought into it, but it's one of the less obvious things that if you do that star on strings is concatenation. I think I have that somewhere down here, 3, 4. Yeah, star is concatenation. So it's concatenating with itself once, and you get 3, 3. Now, as a programmer, I don't necessarily want that. Because if I've defined something to square things, maybe I only want to square integers, or more generally, I only want to square numbers, but we'll get to what a number is later. So someone's told you that there is this type called int, and I can set my function to only square ints. And you sort of see, spoiler alert, what's going to happen here. But I can say x has to be an int, and this function has to return an int. That's what this one means out here. This one's x is an int. This one's the return has to be an int. And then I do the same thing otherwise, and run this one. Squares 3 just fine, but now I try to square the string, and it's like, huh? I don't know how to square strings. Throws an error. And this is really useful when you're writing something big and complicated and you want guarantees that you're passing the right things to the right places. Really often in Python, you're going to have this issue where you have a type mismatch, and unless you like put an assert in there explicitly for, I know, assert this is a float or assert this is a string, it's not going to get caught till somewhere really weird downstream, and you'll get something like, I can't shift bits on data type str, and you're like, what? When did I try to shift bits? And then you'll find, oh, it's because strings have this behavior with this operator, but ints have this behavior with this operator, and it's just really big and complicated. None of that here. This is, again, more in line with something you'll see in like more mainstream for code bases, I guess, programming languages. Well, not to say Python is not mainstream, but a lot of other languages do have this sort of type assurance. So it's nice to have it here. Okay. It's not specified to, these input and outputs don't have to be the same thing. I can say x is a 64-bit floating point number, and I have to return an int. I can also specify if I want an int 16, 32, or 64. And then I have to round the output, because if I don't round the output, then this will cause an error. I could just return x squared, and if I put in 2.25, that's going to give me some float on the other end. And then it'll see, well, I got the right input, but then I got an output, and I tried to cast that to an int 64, and I got confused. So then I have to round it, and now we're fine. Okay, so that's how you guarantee that things have the right types in Julia. Okay, next up is type trees. We've sort of touched on this already with me talking about everything's in general a number, and you can specify to your desired level of detail. And the way you check these relationships is with this operator. That means you can basically read it as is a float 64 is a real number is a number. And there is also the is a operator. So I can do like is a int 3. I think that was the right order of them. Wait, it's 3 int 64. Yeah, and that'll return true. And I can also just look up the documentation. So this is the same thing as like help in Python for getting doc strings of functions. Anyway, so I see a float 64 is a number, but a string's not a number. And someone on Stack Overflow wrote this function to visualize the type trees of things. And so if I have a number, it can be complex or real. Real numbers can be floats of these types. It can be irrational. It can be an integer. Yeah. Is this thing a kind of that thing? Exactly. A number is not a kind of int, but an int's a kind of number.
It's like it's kind of like a less than sign.
Yeah, it's an is contained in, sort of. Yeah. So you see there's all these different types of numbers, and I can operate in general, I can operate on like specific ones of these numbers, but the real power of Julia is in writing things as generally as possible, as we're going to see in this next section. And just for fun, let me try and I haven't tried this before, but let's look at the subtype tree for strings. Oh, there's nothing. Yeah, but if you wanted, you could. I know I do mostly numerical things. Anyway, never mind that. So this one is not a complex type tree. There is nothing that is like a string, but it's not, or as a subclass of strings. But if you wanted, you could imagine something like that. You couldn't actually subtype string because of abstract concrete issues that aren't really important for us right now. But you could imagine doing something that walks like a string would and has some key differences. Okay, so I've got this whole type system. I've got numbers can be all these different types of numbers. How do I actually put it into use? Let's say I made this thing that gives me the 2D rotation matrix. And if you haven't seen this before, it's basically a transformation that takes like a vector in XY space and rotates it. So we'll see right here what that looks like. And so one neat thing about multiple dispatch, or about, I guess, one neat thing about writing these things as generally as possible, also note how this has theta as like actual data characters, which I can write like this. I do /theta like I would in LaTeX, and I hit tab, and it renders as theta. It's really cool. Okay. If theta can be a number, it can be any kind of number. I could put in a complex number because I saw up here, hey, complex is in the number tree. And I just said this has to be a number. So I can do this. And this isn't like special functionality. Python does this too. And if you run the same thing in Python, it'll give you the same answer. But it is cool that you can do that, and that won't break these type invariants that we've set out because we set them pretty generally. Now, suppose we want to use this rotation matrix to rotate a vector. In the comment over here, I've written how you do that in Python. You'd specify I want the rotation matrix of np.pi/2. I define, it does that you use emojis as variable names. Anything legal in Unicode. I've seen like dynamical system simulations out there with like populations like foxes and rabbits that use like fox emoji and a little slider on the fox emoji, and rabbit emoji and little sliders on the rabbit emoji. I don't know how to include those.
This is disturbing. As someone who's had to write text parsers, Unicode is scary.
Unicode's scary, but it's neat to be able to do it. Yeah. Anyway, if you want to scare Alid, write all your homework 4 and 5 emojis. I dare you. If we had extra credit, this would be a great place to give it for entirely emoji-based answers. Anyway, yeah. So getting back to the point, you'd specify you want a rotation matrix, np.pi/2. Then you'd specify the array, which is like np.array, and it's a 2D list, and it's got np.square roots in there, and then you have to do an np.matmul over the whole thing. And here's the Julia. It's just so much nicer. It's so much cleaner. I specify I want a rotation matrix pi/2. I use the character pi because character pi actually renders to what I want, the actual constant, with the ... too, very nice. I can do the actual square root sign. And it really just feels like I'm writing math in a slightly specific way so that the computer can do it. It doesn't feel like programming, I don't think. Okay, it's how you get a negative score with added, but I will give you all the points so it balances out. I'm really annoying him right now, aren't I? Okay, but then the cool part is this star that we used here is the same star that does these operations, that multiplies these numbers, that adds these strings together. How does one operation have all this power? And in fact, you can use the methods method, very meta, to look at all the things that any particular thing can do. And you see there's 364 different things that this star can do, depending on what the inputs are that you put in. I can put in 2 float 32s and I get a float 32 out. I can multiply a complex Boolean by Boolean. I don't even know what a complex Boolean is, but it's cool that I can use it. And I can go look up the specific point in the actual Julia GitHub where they define that and see how it works. I can define it as the star operator in regex, which is another cool thing that we might get to in the end. There's all these things that star can do, and I don't have to care about any of it. And this is exactly the power that lets us compose differential equations with measurements. Because star dispatches in this way, I just have to make sure that I know how to multiply measurements together. And then I have to make sure that a measurement is a number. And that's it. Okay. So let's go through a quick example of overloading. I could now, instead of doing square underscore the type or whatever, I can just say I want to square numbers by doing things squared. And I say I want to square strings by adding the word squared to the end of the string. And now I see I've got square generic function with 2 methods. I know 2 things. I know how to do 2 different things with square. I can square a number or I can square a string. And now they both work under the same name. I don't have to do any complicated like if-else switching like I did in the Python. I can use the same name and it'll do multiple things, multiple dispatch. Okay, and let's take a quick look at measurements. So this using command is like a Python import. This is a subtle difference between a Julia import and Julia using, but you just use using. And we can now look at the subtype tree of number, same as we did up there, and you'll see an extra thing. Measurement got added under abstract float. Cool. So I know now that a measurement is going to mostly play by the same rules as floats. Anytime I would want a float, I can just use a measurement as a drop-in thing, and it'll work just fine. And to support this, a lot of Julia functions out there have written not to specify to float 16, float 32, float 64, but they've written it to work on abstract float types so that I can add on my own concrete float type of measurement over here. And maybe I'm curious about what a measurement is. It's something with a nominal value and an uncertainty, and it defaults to 0 if I leave it out. And here are some examples of how to use them. And this is also a really nice thing of syntax that I already pointed out. I can just do a plus or minus bar. 1.0 plus minus 0.1. Now I can square it as a float, but oops, it's not a float 64. And when I defined square float, I didn't know I could do this whole thing with dispatch. So, and that's because this isn't actually a float 64, it's a measurement that wraps a float 64. So 1.0 and 0.1 are themselves float 64s, but the measurement is its own new thing. So our 2 options are either I have to define how to square a measurement specifically, or, and this is the better, more Julian way that lets us do all this composition, I can define squaring numbers generally and just trust that the person who implemented this caret operator, or they implemented star, and that implicitly defines the caret operator. And so now I've got the square on numbers, which I think I had above anyway, but yeah, I can square anything that is a valid number over here. I can square an int, I can square a float, and I can square a measurement. Boom, I had to add like no code to do that. I just needed the basics, and then I can build on them just seamlessly, thinking of them in exactly the same way that I think of the built-in data types. And that's the real power of Julia. Okay, we're out of time, but here is a really quick thing that I think will only take a minute. If you want to do a bunch of operations in sequence, and this is a real operation that came up in one of my projects, this sort of looks illegible. Like I have to generate a random array, I have to take its length, I have to take its log2 ceiling, cast it to an int, take 2 to the power of it. There's a lot of things going on. And so you have the pipe operator, which is carried over from bash, from the language that you'll write in if you open up your terminal, where I can just pass things through. individual operations at a time. So this will mean the same thing, but it's a lot easier to write. Yeah, the language does have such a great name, Julia. I agree. Yeah. And here's a really quick thing for how you pipe with things that take in multiple inputs or don't take in like single inputs at a time. You just put a blank over here. Yeah. Also, the language isn't like named after anyone. They just all got together and were like, this sounds pretty. So that's kind of nice. Okay. We are out of time and I'm through with everything I want to talk about. So I'm going to stop the recording now.